Well, one thing I wanted to remind everyone of are the lecture videos from the class are posted here. It's just going to stay right here in this announcement. So there's the link for the lecture videos if you need to catch up, or maybe you need to hear something again. That's where they'll all be with that link, just so you're aware of that.
It's a plug-in.
Oh, okay. Close this door.
Important.
Oh, does it automatically go to the page?
Yeah, I think exactly. I'm like, yes, I know what that is.
I shouldn't be taking that.
Yeah, it's just this add-on right here.
That's pretty great.
That's so funny.
Yeah, it's changed my life.
It's changed my life.
Yeah. As a reminder, next class meeting, we don't have class. Okay. That's for all classes. The college is no classes on Tuesday at all. Okay. Any homework questions?
It's not a homework question, but what do we need to start doing on Thursday? Like next Thursday?
Next Thursday, we'll finish 2.5 and start 2.6.
Okay.
That's good.
All right then.
I'm gonna start pumping cold caffeine. Drinks 3 bucks, or is this still?
All right, so in 2.4, we were looking at limits at infinity. Or sorry, infinite limits. Limits at infinity are in 2.5. So here we're talking about basically the calculus version of determining vertical asymptotes for a given function. And we looked at one example on how we compute those. I mean, some of these are like relatively simple to graph, but again, we're moving away from having to rely on a graph to answer questions. And since we're defining a vertical asymptote in the sense of a limit, we want to be able to use the limit procedure to determine where those are. And so in order to do that, I guess there's a few ways to think about it, but the way we're talking about it here in class anyways is we're just going to look at the values. Well, let me back up. We're going to look at the function itself, and knowing something about that function can be really, really beneficial when we're computing these types of limits. Because sometimes you run into a limit where we can factor and simplify, or we can, conjugate and simplify, right? We're just saying, like, after all of that stuff has been exhausted, and we're still staring at this limit where the denominator is approaching 0, then knowing about the function can really help. So you're not wondering, well, I tried to simplify and nothing works, I really don't know what to do at this point. Usually you're in this place where you're approaching a vertical asymptote. Okay. So for the example of 5 plus x over x, we just said, well, what does the numerator approach as x approaches 0? And what does the denominator approach? So the important aspect, the thing that actually gives us that infinity as the result of that limit, is the fact that the denominator is getting smaller and smaller while the numerator is fixed. So anytime you have that situation, the numerator is fixed, but the denominator is approaching 0, it will be infinity or negative infinity. Is everyone clear on that? So the idea is then, all right, well, are we approaching 0 through negative values or positive values? Because that determines the sign of the infinity, positive or negative. Okay, and that's what we did here. Did anyone have any questions on the 5 plus x over x example? All right. So in the sense of this function, 5 plus x over x, I have enough room here. Yeah. What it's saying is if I were to look at the graph, I only know a little bit of information about it so far with this limit. But x is approaching 0 from the left and from the right. As I approach 0 from the left, my function values dive off to negative infinity. So, whatever my function's doing, it's not doing that. But whatever it's doing, I know that when I get down here, It's going to die off towards negative infinity from the left of 0. And then what we computed in part 1, as I approach 0 from the right, the function's approaching a positive infinity. So whatever the function's doing over here, I'm not quite sure yet, but I do know as I get closer to 0 from the right, the function will approach positive infinity.
For exams, how complicated are those graphs going to be? I guess the only reason I asked is because, like, a lot of times on the homework, I'll just build the graph like in Desmos,
Okay.
and then get the answers either from calculation, if I can, or just by looking at what the trend in the graph is doing.
Okay.
You know what I mean?
Yeah.
So there's not a lot of conceptual effort to mentally build what that graph actually looks like.
Yeah.
I'm not sure how that'll potentially.
Well, we'll look at a couple of examples, or maybe one other example here in a minute. I would say that if you're using graphs to answer these questions, are you talking about this section specifically or in general?
Mostly just this section, especially some of the bigger ones like the quadratics. But I'll see if I can simplify it in any way. But you know, if it's one that can't be simplified and it's got squares or cubes in it, I'm probably just gonna go build it real quick and.
Yeah. So the problem is you couldn't do that on the exam, right?
Not comfortably.
Then you got to rely on the analytical method
Yeah.
to look at that. So,
Okay.
you know, in this section, if you're asked to compute these limits and you're graphing them, I say that's fine as long as you've worked the problem, right? So if we want to look at the graph to say, well, did we do that right? Yeah, as we approach 0 from the left, this function's negative infinity, and from the right is approaching positive infinity. I think that's fine to check your work. Somehow you need to figure out how to analyze these things without looking at graphs, because two things. One, the graph isn't provided on the exam, and two, with the more complicated functions, it's going to be really time consuming to graph. So if you want to look at numerics or think about it how we're thinking about it here, either way, but don't rely on a graph to answer questions. You can use them to check, but well, let me go ahead and put this in our notes too. Just so it's a little bit cleaner. We'll look at another example that's a little simplified, just so we can get the idea, and then we'll look at maybe one or two more complicated rational functions. So the limit as x approaches 0 of 1 over x squared, and in fact we did see this at the very beginning. We saw a table of values and we saw a graph for this, but something like this is pretty simple to graph. But the way we want to think about it is, okay, well, I'm asked to compute the limit as x approaches 0 on 1 over x squared. There's no simplification takes place there. So what I'm dealing with is an asymptote, right? I have a vertical asymptote. There's no factors canceling out. So then I need to look at a one-sided limit from the left and from the right. And as I look at that, I say, well, as x approaches 0 from the right, my numerator is 1. And us approaching 0 from the right, what happens to this x right here in the denominator? What does it approach? 0, right? So remember, you never just want to put 0. We have to determine through what values of 0 it's approaching. I know this function's a little bit different because we have the square, but we still need to be able to determine that we're approaching 0 through positive values of 0. And don't get into the habit of matching the superscript, I'm approaching this thing from the left or from the right. It's not always the sign on your zero. You really have to think about what's happening in the problem itself. Okay.
Say that again?
So this superscript right here
Right.
isn't always the sign or the value that you're approaching zero through.
Oh, I see what you're, okay.
So a lot of people make that mistake, and it's just absolutely not true. And we've seen a couple of examples where it is, but it's usually not. Okay, so we're approaching zero through positive values. I've got a fixed numerator whose denominator is getting smaller and smaller, which means my fraction is getting, or which means the quotient is getting larger and larger, right? Is everyone okay with that concept? That's really like the key thing to realize here. So let's just write one more step. Since I'm approaching zero through positive values and all of those values are getting squared, I'm still approaching zero through positive values. Therefore, the function values are approaching positive infinity. We've got a positive 1 over very small positive values. Yeah.
Are we going to be looking at an example where the signs don't match?
Yeah, I think I have one.
Okay.
I think. So that's really how we want to think about these things. And if you want, you can take 1 over 0.1 squared, 1 over 0.001 squared, 1 over 0.0000001 squared. But if you're doing that, like I said last class, make sure you realize that this function is actually going off to infinity. It's not going off to 10 billion. It doesn't stop there. It keeps going. All right. So we've got a similar thing happening with x approaching 0 from the left. The numerator is still approaching 1. This time, though, our denominator squared, the x is approaching 0 through negative values because we're to the left of 0. So those are all negative values. Still approaching 0, though. So here, with the square, takes care of that negative. So it's 1 over really small positive numbers. And so once again, this limit approaches infinity. And then when we look at the graph of that function on the first page, it totally matches. 1 over x squared is doing this. So here's what we've determined. As I approach 0 from the left and the right, my function is approaching infinity. Remember, these limits don't exist. It's just giving us a description of what's happening on the function. Where are the arrows at on the function, basically, is what we're finding. Okay. So any questions on what we're doing here? Yeah?
So why is that a positive 0?
Because we had to square it. So small, we had, initially we're passing through small negative numbers, but those small negative numbers got squared.
So if it was cubed, it'd be negative infinity?
Yeah, if that were 1 over x cubed, that would be negative infinity. Yeah, any other questions? All right. So something a little bit more involved. I'm going to skip this example just for time, but this example I think is a little bit more simple than this example. So we'll work example 2, and if there's any questions or issues, we can perhaps go back to that first one. So I'm asked to compute the limit as x approaches 2 on the given rational function. Now, initially what I see is that, well, if I plug in 2, I'm dividing through by 0. But if I'm dividing through by 0, does that always indicate that I have a vertical asymptote there? No, and we know that just from a pre-calculus standpoint. In order for it to be an asymptote, it can't cancel out with a factor on the top, right? So that's what we should do here. We should factor the numerator and see, does anything cancel before we just assume that it's a vertical asymptote. Yeah.
Why wouldn't we try direct substitution first?
You can try direct substitution, which is what we do when we evaluate a limit. We just plug stuff in. But this one, since the denominator is already factored, like it should be obvious that there's issues with that, right? Because when x is 2, then that's 0. The whole bottom is 0. So in our minds, we directly substitute. Oh, I divided by 0. That's a problem, right? So we'll factor the top and then see what we're actually dealing with. So what is the limit as x approaches 2 when we factor the numerator? The numerator factors how?
X minus 2, x minus 3.
We have x minus 2 times x minus 3. So what happens in this instant is that these factors divide out, and so that original limit is equivalent to computing the limit as x approaches 2 on the function x minus 3 over x plus 1. And so can we compute that limit? Yeah, what's the limit for this one?
-1/3.
-1 over 3. Right, exactly. So we approached a number that wasn't in the function's domain, but we get a finite number in return. So that's a hole there. And again, from an algebra perspective, we would say, well, if that was f of x, I just deleted this factor or removed this factor. So that removal of the factor causes the function to have a hole there, right?
And how is that to find that whole definition, x minus 2 equals 0? Find
The coordinate of,
Yeah.
so the coordinate is kind of implicitly given to us because x is approaching 2. We have a hole at 2, and the y values were approaching a -1/3. So I'm just bringing this up to tie into previous stuff, just so we don't get accustomed to doing limits in 2.4 the same way. Just everything we've talked about is still applicable. Okay, so maybe that's part A for 2. We'll call this part B. Let's compute the limit as x approaches -1 on the same function. Is everyone okay for us to just write out the reduced function? Because if we wrote out the full function, we would then factor it again and simplify it. So, whether we write out the original or the reduced, we'll end up here with x minus 3 over x plus 1 anyways. So it's just like in prior courses where when you see a function like this, you want to factor the top and bottom before you do anything. If it reduces, fine. You've got a much simpler function to work with. If it doesn't reduce, then that's okay. We can still look at it. At least we know what's happening through that process of reducing. Okay. So same sort of issue here, right? X is approaching -1. The denominator is approaching 0. So that means what's happening? What's going on there? A what? Infinite, sorry, say that again? Yeah, infinite limit. Because that factor of x plus 1 we saw didn't go away. So we had a hole at x equals to 2 for the factor that went away. The factor that remains in the denominator that doesn't get simplified is our vertical asymptote. So in order to compute this limit, we need to look at what happens as x approaches -1 from both sides. So the limit as x approaches -1, let's do from the right, on x minus 3 over x plus 1. So Just take a minute or two and think about that. What is that approaching? I mean, we already are clued into the fact that it is, or should be, infinity, but we've got to now determine what's the sign. Is it approaching positive or negative infinity? Just think about that for a minute. So anyone care to share what they think?
Would it be negative infinity?
So would it be negative infinity? What do y'all think? Unsure, maybe? So what's the numerator approaching? -4. Denominators are approaching 0, but through what values is the denominator approaching 0 through? Positive, right? Because if you have to draw a little picture here, that's fine. Just do it. Here's -1. I'm approaching -1 from the right. So here's 0. And so really what we're doing is we're just adding all of these numbers, in essence, to the +1 in the denominator. So if I take any of those numbers that are to the right of -1 and add them to 1, then they'll always give me a really small positive number, right? Because these are like -0.999 and so forth. So all of those numbers added to 1 give us a really small positive number. So then we just look at, well, since the denominator is approaching 0, that's going to give me infinity. Well, what's the sign on infinity? We're just going to look at these signs here of the entire fraction. We've got a negative over a positive, which gives me a negative. Does that make sense? Does anyone have any questions on it? It's really important that we're on the same page. If you don't want to ask questions or if it doesn't make sense, then if you're looking at something else online, they might explain it a little bit differently, but it's still the same idea. Okay. Yes.
So where did you get the positive part for the numerator, or for the 0?
For the 0,
Yeah.
because as x approaches -1 from the right,
Right.
we're approaching -1 from this direction.
Okay.
And then all of those numbers are kind of like that, right? They're all like really small, negative, not quite 1. So anytime we take any of those numbers and add them to 1 there, they're still going to be really small and positive. So that's really small and positive. All right, so how about the limit as x approaches -1 from the left? Positive infinity? Well, nothing's changed up top. It's still approaching -4. Denominator's still approaching 0. Through what values of 0 are we approaching through? Negative values. Here's -1, here's -2. We're approaching -1 from the left. And just write a number down or a couple of those. It's -1.0001, for example. So when any of these numbers are added to +1, those are going to be very small but negative. So the infinity, again, comes from the fact that the denominator is getting smaller and smaller, and the sign is now a negative over a negative, which is positive. and we'll look at the graph for verification. Sorry, I'll go back to that. So there's verification of what we've done here. As we approach -1 from the left, our function's values are getting larger and larger. And as we approach -1 from the right, the function values get smaller and smaller. Any questions on that? So you do, when you're computing these limits, if you've got like two factors up top, you have to just multiply that out. You have to know what the sign of the infinity is, taking into account everything that's contributing to the signs, right? So if you ended up with like a -2 on top times 3 times -5 all over like 5 times this factor approaching 0 through negative values. Then you have to look at the top. The top is negative. We'll just negative number here. The bottom is approaching 0, right? 0 times 5, still 0. And then we have to look at the negative times the positive here. So this thing is approaching positive infinity. You have to take like everything into account.
Wouldn't it
Be positive on top.
positive on top?
Oh yeah, positive on top, my bad. Yeah,
So then we're
thank you.
approaching
Negative infinity.
Okay.
Yep, thank you. So you just make sure if you've got multiple factors that don't go away, that you're examining their value as well. Does that make sense? Okay. I sort of skipped over this. We talked about it briefly, but whatever. I think that's page 4. Just as far as our notation, like I said, it wasn't standard, but that's what we mean is you can write it out too. You can say this the bottom or denominator approaches 0 through positive numbers. It's just if you have to write that out a lot, it just gets kind of tiresome. So when we write something like this, we just mean the denominator is approaching 0 through positive numbers. In other words, what we're saying here is that these are just small positive numbers. If you want to write all of that out, I'm totally fine with that too. And here's small negative numbers. Just so there's not any confusion on this weird notation we're using. Okay. And so the same ideas applies to these trig functions as well. So let's say we totally blanked on what the graph of cotangent looks like. And we want to compute the limit as x approaches 0 on cotangent. And so they say, all right, well, compute the limit as x approaches 0 from the left and from the right. So I guess if you have a calculator, you can just plug stuff in, but I'd rather you not do that. I think it's much more beneficial to be able to analyze these things. I don't know that I would say 100% of the time, but almost every time you have these kind of, cotangent, tangent, secant, cosecant functions, I think it's a lot more helpful to think about them in terms of sines and cosines. So let's think about cotangent in terms of sine and cosine. So that's the limit as x approaches 0 from the left. And cotangent was what?
Cosine over sine.
Yeah, cosine over sine. Now, when we think about it as a quotient, that kind of puts us right back to how we were thinking about the last three examples. What's the numerator doing? What's the denominator doing? So as x approaches 0 from the left, what does cosine approach? 1. And if you forgot, you probably should know the basic graph here. Not really to scale, but this is cosine x. You should know these values. Here, here, here. So as we approach 0 from the left, it keeps going. Cosine is approaching 1. What about sine? It's approaching 0, yeah, through
Negative values.
negative values. So here's sine x. And as we approach 0 from the left, we see that the sine function approaches 0, but all of these values that we're approaching 0 through are negative. So what is this limit then? Negative infinity. Numerator's fixed, denominator's getting smaller and smaller. That gives us our infinity. The fact that we have a positive over a negative gives us a negative here. So we forgot about cotangent, but what do we now know? What happens on the graph of cotangent near 0? It's undefined because the graph of cotangent has a what at x equal to 0? A vertical asymptote, right? Remember, that's the definition of a vertical asymptote. If we approach a finite number, but the function values approach infinity, that's automatically classifying that x value as a vertical asymptote. Contrast that to when we approach a finite number and the limit comes out as a finite number, then we say there's a hole there. It's just kind of the other side of the picture. Holes versus vertical asymptotes. So we're going to think of answer this limit question here the same way we answered the previous one. We're going to think about this as cosine over sine. Cosine is still approaching 1 as x approaches 0 from the right. Denominator, again, still approaching 0, sine still approaching 0, but this time through positive values. Because we're approaching 0 from the right, we have to approach through these values here, and these are all positive. Let's get this. So as x approaches 0 from the right on cotangent, the cotangent function approaches positive infinity. And so, at least we know, like, in a certain part of that graph, what's happening. We know how it's doing, as we get closer to 0, what's happening there. Anybody have any questions on that?
So since it approaches from the right, is that the sign that carries over to the 0?
You mean this thing and this thing?
Yeah.
No, that's not always the case. The reason this was approaching 0 through positive numbers is because on this function, as we approach 0 from the right, those are all positive values. Yes.
So does cosine not go towards 0 because it's passing through, like it doesn't go through the origin, or because?
Yeah,
Okay.
exactly. Yeah, because the issue doesn't lie with cosine, right? Is cosine just think about cosine evaluated at 0 is 1.
Okay.
So whether we approach from the left or the right, it's still approaching 1.
Okay.
The only time we want to think about what values am I approaching through is the factor or the factor in the denominator that's giving you 0. That's the only one you think about. All right, well, am I approaching through positive or negative values? So with these trig functions, it's helpful to write them as sines, cosines, and then remember these two graphs. As I approach 0, what values am I approaching through? With the rational functions, I think it's just easier to think about them numerically. All right, like the bottom factor was x minus 1. I'm approaching 1 from the right or the left. What's happening to these numbers in terms of the factor x minus 1 or whatever it is? I hope that makes sense. Does anyone have any other questions? So again, visual verification of what we've just done. So we've got the limit from the left, negative infinity. The limit from the right is positive infinity. What would we say about the limit as x approaches 0? It does not exist. We could have said that immediately after just computing one of those. We didn't have to compute both of those. I will say though, however, in the sense of when we had the 1 over x squared function, if we go back and look at that, the limit as x approaches 0 from the right, and the limit as x approaches 0 from the left. Was also infinity. In this sense, we could technically, I'll just write this out and talk about it. Okay. So really the issue with writing that, it's fine since both of these approach infinity. It's sort of misleading, I think, because it's if we look at this two-sided limit and we say, well, that indicates that I can approach 0 from both sides and approach it, and the functions approach infinity, right? But we know that it's a little bit more technical than that, because we know that there's a vertical asymptote here. So in that respect, it kind of makes sense, but in another respect it doesn't, because one-sided limits are appropriate anytime you approach a vertical asymptote. So if when we're writing stuff like this, just think about it more visually like this. I know some of these limit laws or limit things we've talked about aren't necessarily consistent throughout. And that's usually the case with most of the stuff we do. It's very particular to the context you're in. What are you actually dealing with? So that's why it's really helpful to know, in this particular function, is it an asymptote, is it a hole, what is it? And if you forget, hopefully you can just work the limits like we've done and determine, hey, that's a hole because I approached a finite number and the limit's finite. Or that's a vertical asymptote because I approached a finite number and the limit is infinite. So I think we have like two sets of knowledge. One we're a little bit more familiar with, we can default to, but one we should be focusing on more that we're not as familiar with. Okay, so just wanted to mention that. We'll look at this last example from 2.4. And this will bring up a concept that we look at later in, or that does come up later in chapter 3 as well. But now with what we've done in 2.4, we sort of have the means to talk about this now. So we're given the function x to the 1/3. Find part A, find the secant line, or the slope of the secant through the point 0, 0 and h comma f of h. So our reminder again, how do we find the slope of a secant line? Yeah. Right, the change in y over the change in x. So these are the 2 points they've given us. Let's just look at the change in y over the change in x. Okay, so that's just f of h over h. Can we simplify that more? What's f of h? It's a y value. I agree.
Can you plug it into the function and like determine what f of h really is?
Yeah. If I ask you what's f of 0, what would you tell me? 0. And how'd you get that? Just plugged it into the function, right? For x equals 0. So if we need to evaluate f of h, then we'll just plug h into that function. So we can evaluate f of h because we're given the definition of the function f. So that's just h to the 1/3 over h. And then we can simplify that as h to the negative 2/3. And so that's it. Or we could write this with positive exponents. 1 over the cube root of h squared.
Why did you put h to
Up top, because all we did was took this h and plugged it in here.
Oh. So it's assuming f of h is like right in here.
Yeah, because this, again, these things read, this is like f of input, right? And then I have my input to the 1/3. So if I plug in h or cube or star or spaghetti, right, like I have a means to compute that.
And then how did you get the negative?
The negative what?
The h to the negative 2/3.
Oh, so powers or properties of exponents here. This is h to the first, so we subtract.
That's right, okay.
You're welcome. Okay, great. What does that even mean? Well, we know it's the slope of the secant line between these 2 points, 0, 0, and h, f of h. But again, what is that really, like, what is that? maybe it's more meaningful if I said, okay, well, what if h is 1? I'm going to end up erasing this. You can put it in your notes if you want. But if h is 1, then I have the point 0, 0, and what else? 1, comma, f of 1. So what's f of 1? 1 to the 1/3 is 1. So if h is 1, it says, well, what's the slope of the secant line between those 2 points? Since h is 1, all I have to do is plug h equals to 1 into that right there, right? It's very, very comparable to that homework question from 2.1 where it said, okay, now find the average rate of change on the interval 1 to 1 plus h. Does that make sense? It's sort of giving us a shortcut. So if I said, well, what's the slope of the secant line or the average rate of change between 0 and 1? Without this notation up here, we would say, well, that's f of 1 minus 0 over 1 minus 0, right? That's the slope of the secant line. And then if I said, well, if h is 3, then I've got the points, again, 0, 0, and 3, comma, 3 to the 1/3. And you say, well, I got to find the slope between those 2 points. So it's 3 to the 1/3 minus 0 over 3 minus 0. And so we have to compute those every single time. Instead, what we have is a formula for, basically think of h as just a distance that you are from 0. So I'm from here to here, I've just moved 3 units in the positive direction. H is 3. To compute that the same secant line there, all I have to do is plug 3 into this here. Is that clear? Clear as mud. Or a lot of stuff. So really, that's a way to characterize or generalize the slope on this function x to the 1/3. I'm starting at the origin, and any point that's away from the origin, I can find the slope of the secant line, as long as I just describe the distance from the origin. So that's a function of, it's the slope of the secant line as a function of the distance from the origin. Okay. Part B. I'm going to move that up. There's a lot of empty space. So part B has us calculate the slope of the secant line as h approaches 0 from the left and right, and then interpret those results. So maybe taking a step back to what we did in 2.1 can sort of help us interpret the results. So it says, take the secant line, or slope of the secant line rather, and look at as h approaches 0 from the left and from the right. So that, of course, is in the context of the limit now. We'll maybe write this down again, but if I compute the limit, you know, whatever, here it's h approaching 0. If I compute the limit on the secant line here, what is that going to give me? Or sorry, the slope of the secant line.
0.
Well, it's not going to be 0. Just like, let's ignore what we're doing in this problem altogether. If I attach a limit to the slope of the secant line, what will that give me? If I attach the limit to the average rate of change, what will that give me?
Slope of the tangent line.
The slope of the tangent line, or the instantaneous rate of change, right? We did that in 2.1, where we looked at a whole bunch of slopes of secant lines and then saw what happens, do they approach something specific? And we said, well, in order for them to approach 64, then what had to happen was the time values had to get closer and closer to 1, right? So when we compute the limit on the slope of a secant line, whatever we're approaching, in this instance it's 0, we are calculating the slope of the tangent line at that location. So we're asked to compute two limits. Now remember, from part A, we found that the that the slope of the secant line was given to us as 1 over the cube root of h squared. Yeah. Not quite. We'll see what happens here, but so like a vertical asymptote, you're thinking in the sense of a vertical asymptote. When you just look at this limit by itself, that I assume that's what you're looking at, right? If we compute this limit, then we're going to get infinity. So yeah, let's talk about that, because it's not quite. Because this right here that we're computing came from a different context. It's not just the function itself that we're dealing with. So as h approaches 0 from the right, what does 1 over the cube root of h squared approach?
Negative infinity?
Negative infinity? What do y'all think? Negative infinity for this part 1?
Positive.
Yeah. So the numerator is approaching 1. H is approaching 0 through positive values, right?
Oh,
Zero.
shit, I'm sorry.
Zero.
I thought you were approaching.
Yeah, no, it's totally okay. Honest mistake. I mean, I just said two negatives multiplied by each other were a negative. So. Yeah. Okay, so 0 through positive values, that's getting squared, and then we're taking the cube root, so it's 1 over the cube root of a small positive number, which is a small positive number, which is positive infinity. Questions on that? Okay, so based on what we've done, we might look at that and say, okay, well, that function has a vertical asymptote. But that's not true, because what we're computing the limit on the slopes of the secant lines, which we know that this gives us the slope of the tangent line, right? So whether we're dealing with this problem or not, you take the slope of the secant line, put a limit on it, it turns into a slope of a tangent line. So the function, if you will, that we're dealing with is 1 over the cube root of h squared. That wasn't the original function. The original function was x to the 1/3. So we wouldn't say, well, this limit means that x to the 1/3 has a vertical asymptote, because we're not even computing the limit on that function. If we wanted to know about what happens on the original function x to the 1/3, then we need to compute limits on that, right? I mean, we have to interpret our results, and it's going to be the same for each limit, so we might as well interpret our results, since we've already said that if I compute this limit, I get the slope of a tangent line. So I'm just going to do that in a different color here. And so what does that mean for us? How do we interpret what we've just done?
The tangent line is vertical, it's not vertical asymptote.
Right, good, yeah. So we have the tangent line, the slope of the tangent line more specifically is infinity. And then when we think about a line, what kind of line has an infinite slope?
Just a vertical line.
a vertical line, right? So this is the slope of the tangent line. Let's say this. That is the slope of the tangent line is vertical as h approaches 0 from the right. So maybe let's make a little bit more sense of as h approaches 0 from the right. Remember we had the 2 points, points 0, 0, and h comma f of h on the function x to the 1/3. Is everybody all right with that? The tangent line slope is horizontal as h approaches 0. So what we're trying to do is make that a little more specific. Well, what happens as h approaches 0? We were given these 2 points on x to the 1/3. So as h approaches 0, what happens to this point right here? What does that point get closer and closer to if h approaches 0? The point itself. I promise it's not a trick question.
Oh, it's getting closer to 0, 0.
It's getting closer to 0, 0, isn't it? If h is getting closer to 0, doesn't this h get closer to 0? And doesn't this h get closer to 0, f of h, or sorry, f of 0? So we're getting closer and closer to the point 0 comma f of 0. Okay, that's a little bit more descriptive. But what is f of 0? 0, because f of x was x to the 1/3. 0 to the 1/3 is 0. Yeah?
There's just kind of something I'm confused about. So the secant line is kind of, we're talking about it's like the average increase, like the average slope of whatever.
Yeah.
What exactly is a tangent line? Because I know it's just a line, right? It's just a point on the graph.
Yeah, so
What is that, like, what does that mean?
right, so the average rate of change was for the secant,
Yeah.
slope of the secant line. The slope of the tangent line is the instantaneous rate of change. Yeah, and we wrote that down in 2.1 as well, if you didn't remember, which is fine because we've written a lot of stuff down. I don't blame you for not remembering. Yeah, so it's like if I'm driving to school, remember it takes me about, on average, I'm going 30 miles per hour, but when I look down at my speedometer, I'm going 65 miles an hour. Your speedometer readout is your instantaneous
So
velocity.
At that moment.
Yes, right.
Okay.
Yep. So yeah, the way we classify when we speak about average rate of change or the slope of the secant line, those are one and the same. And when we speak about instantaneous rates of change or the slope of the tangent line, they're one and the same. One's more of a physical context, one's more of a mathematical context. Okay. All right. So what we're saying is, since this limit is infinity, that limit on the slope of the secant line is giving us the slope of the tangent line, which meant the slope of the tangent line is infinite, which means the slope of the tangent line is vertical as h approaches 0 from the right. But what that actually means is we've got a vertical tangent line on the function x to the 1/3 at the point h comma f of h, which was 0, 0 as h approaches 0.
So it's just saying make a straight line at 0, 0.
Yep. Okay, so let's can we put all that together? Meaning, on the function x to the 1/3, we have a vertical tangent vertical tangent line at 0, 0. So those are really the other limit you'll see works the same. I think we'll skip that because it's the same result, it's the same conclusion. So again, that limit that we got to, that we computed as infinity wasn't the limit on the original function, right? It was the limit on the slope of the secant line. If I just looked at this function, from an algebraic perspective, does that function have any discontinuity, or does that function have any holes or asymptotes? No, because you're not taking the even root, nor are we dividing through by anything, right? So let's look at the graph of that function, just so we can kind of visually make sense of sort of this kind of involved process here. All right, so it doesn't look unusual here, but when we start getting closer and closer to 0, let's get as close as we can. I mean, granted, any curve you get close enough to will look like a straight line, but that's kind of the idea. Just think about like a ruler or a pencil sliding across the surface of the curve. That's what your tangent line is measuring. So I'll put this in our notes and look at that for a minute. So if I said, well, at this point, what's the tangent line doing? I don't know, but I can measure that slope, right? And then say, as we get closer and closer to 0, what's happening to the slope of these lines?
It's becoming more vertical.
Yeah, they're getting more and more vertical. And that's what our work has enforced, is the fact that this is actually happening. The other part that we didn't do was just as we approach 0 from the left. So the first set of green lines we actually drew were approaching 0 from the left. But as imagine your pencil sliding across that surface. Either way, it kind of meets up like this, and then it's vertical. So we will look at this a little bit more in detail. You can have the slope being negative infinity, which means that, so the way we interpret that, since we were looking at a positive infinity slope, notice that all of the slopes of any of those green lines are always positive, right? You can approach a vertical tangent through negative slopes. So if I approached a vertical tangent line through negative slopes, that's when negative infinity would show up. I know that's probably not very amazing, but I think it's helpful to put what we're looking at in different contexts, because in different contexts it does have the potential to describe different things. So does anyone have any questions about that? Okay. How about we'll take a break and then start section 2.5.
Which is, oh my God.
Okay.
He passed away the day after.
So now we'll look at 2.5, limits at infinity. So limits at infinity occur when the independent variable, typically x, but t sometimes as well, approaches infinity or negative infinity. And these limits determine the function's end behavior. So some applications are like systems that evolve over time. You want to know, like maybe you've got a model of like an epidemic that's spreading through town. Does that epidemic die off, or does it keep going? And steady states, that's the same kind of idea. So you need to remember this. Whereas limits at infinity determine end behavior, our infinite limits determined vertical asymptotes. And so end behavior in some senses sometimes are horizontal asymptotes. But like we mentioned at the beginning of 2.4, not all functions have horizontal asymptotes. So here's a picture. As x gets large in either direction, do the y values actually approach something finite? And if they do, we say in general that's the function's end behavior. But you know, if a function is, as x approaches infinity, if this function is leveling off, then we also classify that as a horizontal asymptote. So end behavior is just kind of the catch-all for limits at infinity. Okay, so we'll define that. And this is specifically talking about limits at infinity that are equal to a finite number. So note here, we didn't say the limit as x approaches infinity on f of x is equal to infinity, right? We're saying that the limit as x approaches infinity, as x gets further and further out, the function values are getting closer and closer to this particular number, okay? So if, do they say that? If your limit at infinity is finite, then what you're talking about is a horizontal asymptote. But either way, you're still talking about what's happening on the ends. We kind of looked at a similar situation in 2.4, that when we look at a quotient, if the denominator got smaller and smaller, we said that the quotient got larger and larger. Here we're saying kind of like on the flip side of that, if the denominator is getting larger and larger, your quotient gets smaller and smaller. So that will arise in practice. Maybe you remember this, maybe you don't, but can the limit as x approaches infinity not equal a finite number? Can it be infinity or negative infinity? Yeah, and when was our, or what was a function where that was taking place? Quadratic function, cubic function, right? Any polynomial. We all know what those look like. So we're going to talk about limits at infinity, specifically on polynomial functions. Look at how we compute those limits, and then and it sort of builds into computing limits at infinity on rational functions. And then we'll look at more exotic functions after that. Okay, so without even discussing a limit, there was a way prior to this course to determine, in effect, what those limits are. So let's say here, since on polynomial functions the limit at infinity doesn't equal a finite number, we'll say limits at infinity on polynomial functions determine end behavior and again, we'll say here since the limit is not finite. So before calculus, how did we find the end behavior? On polynomials.
Did you just determine positive and negative x values?
Be more specific. What do you mean by that?
I feel like I always remember just depending. I can't remember if the x values were if we would determine them based off the equation, but generally, I thought the quick way that we would generally just do it is look at one or two, including 0, 1 or 2 negative values, 1 or 2 positive values, and see what the y equaled.
Okay.
And just kind of get that general determination of what's
Sure.
happening.
Yeah.
Say whatever your x value was negative, whatever your positive x value was, and just kind of getting a mental image of generally speaking what it was doing.
Okay.
Was it going up, was it going down, was it?
So looking at specific x values. So, like if we had this polynomial and we said, well, maybe it's doing this. Right. So how would we determine the end behavior if we were given that polynomial? And we don't know the graph, but I don't know, maybe we just pick this x value and this x value and see what the y values are doing, right?
Is that just finding the slope, right? Getting 2 points.
Not in that instance. But also the problem with this is if we don't know what the graph looks like, for all we know, this thing turns around way up here, goes way down here, turns back around, and goes way up here, right? So if we're looking at these values, we might say, oh, okay, well, those are indicating that it's going to negative infinity, but in fact, it does turn back around and go off to positive infinity, right? Did someone over here want to add something? I thought I saw a hand. Okay, yeah.
I was going to say the sign on the leading coefficient on x,
Yeah.
and then the highest power on x.
Right.
Would be would determine your end behaviors.
Yes.
Whether it's doing this or this or.
Yeah, exactly. So let me just put a specific example here. For example, what's the end behavior of f of x equals to negative 5x to the 7th plus 4x squared minus 3? Yeah, so remember the end behavior with polynomials is basically like where are the arrows pointing? Are they pointing like this, like this, like this, or like that? Do y'all remember that?
Yep.
Okay, so we said that in order to determine that, all we had to do was look at this term right here with the x on the highest power, look at the degree, and the leading coefficient, right? Does anybody remember what we called that?
The leading term.
Leading term test, yeah. Does that ring a bell at all?
That's not what we called it either, but you know, whatever.
I don't know that that's a universal phrase,
We know what you're talking about.
but it is the leading term, and we do look at the leading term. And then, you know, you might have asked your algebra or pre-calc teacher, like, well, how come we can just look at the leading term? What about all of those other terms that are behind it? What about that x to the third and that x squared, etc., right? And then they give you an answer like, well, as far as end behavior goes, what's happening is that x is going to infinity. And so like the cubes and the squares become less and less significant the larger and larger you go, right? So like if I had 1 billion to the 7th power plus 1 billion squared, it's still pretty much 1 billion to the 7th power, isn't it? So that's kind of the reasoning you were given. But that reasoning, again, is still based off the limit as x gets larger and larger. What happens to the y values? Okay. So the leading term test said that we had to look at the leading term, of course. And then the leading term was made up of two things. We had the degree of the power on x. So either the degree was even, or the degree was odd. Is it hot in here? It's so hot. Would you mind opening that door for me, please? Yeah, open both of them. It's just, it probably won't help, but we can try. Okay, so we have the highest power on x, and then we have the leading coefficient. I'll just put this here, leading coefficient. Leading coefficient, and just for notation purposes, here's our polynomial. Capital P of x is a sub n times x to the nth power plus a sub n minus 1, x to the n minus 1 plus some constant a sub 0. Okay? So we'll call that leading coefficient a sub n. If a sub n was positive, then you had one kind of thing happening. So like if I had a positive x to the 5th versus a negative x to the 5th, you have two different scenarios there. So whether that leading coefficient was positive or negative also played a factor in determining the end behavior or what direction the arrows face. And so if you remember this, you had like 4 outcomes, right? If it's an even degree and a positive coefficient, then it just looks like a, you know, standard quadratic as far as where the arrows are at. Yeah.
Kick is good.
Yeah. What? I've seen mnemonics to remember that.
Like the football referees.
Oh
After the
yeah,
kick.
yeah. Yeah, I guess that's appropriate. But not everybody's familiar with sports references, I feel. So I don't know.
It's a half pipe.
All right. So that's like a positive x squared. What if we had like a positive odd degree, positive x cubed? What does x cubed look like? Where are its arrows?
Down, up.
Yeah. Right. So then that's the end behavior there, and then there. And then when the leading coefficient's negative, things just get reflected across the x-axis. So now this is pointing down, and this one is pointing up, and then this one's pointing down. So 4 outcomes, 1 of 4 outcomes with any polynomial. Okay, so I don't know, leading term test, you seem to not be familiar with that term, but this chart, surely you've seen that at least once. So here, for example, what is the end behavior of the function f of x equals to negative 3x to the 4th plus 5x cubed minus 2x to the 7th plus x plus 1.
No, it's going to be, you have to go to this, but the exponent is 7.
Yeah, so we've got to find the leading term first. Here's x with the highest power. Can I abbreviate leading term like that? So that's our leading term. The degree, the power on x is odd, and the coefficient is negative. So we have that one that really is directly above us right there. Odd degree, negative coefficient. Oops. So there's the end behavior of that graph, or of that polynomial rather. You know, I guess more appropriately, if we were to graph this, and when we did graph polynomials, that's where we started with. That's what we started with. We said, all right, well, on the far left, where's my function starting? This function's way up here on the far left, and on the far right, it's down here. So like, depending on the function I'm dealing with, then we looked at the zeros. Does it cross through? Does it bounce off? We better make sure we end where we're supposed to end, all that kind of stuff. Okay. So then, you know, the natural question is how or why is this allowed? And we kind of already answered that. So the reason that we're isolating the leading term is because now we know the nature of end behavior. What that means is x is approaching infinity or negative infinity. Either way, x is becoming increasingly large. Okay. Because that's what we'll say. As x approaches infinity or negative infinity, the lesser terms the lesser terms don't matter. I'll put this relative, but you can just get your calculator out and see that for yourself. Well, fortunately for us, that's exactly how we compute limits at infinity on polynomial functions. So to compute limits at infinity, on polynomial functions, how do I want to say this? I guess we only need to I guess work with. We only need to work with the leading term. Okay. So that's really the fact that gave us the leading term test. It's not the other way around. The leading term test means that in order to work with limits, no, it doesn't. That's not why. The working with limits is what implies the leading term test, not the other way around. So really, does anyone have any questions at this point? Okay. So then really what that means in practice is and a lot of the things we do is really crucial to recognize what kind of function you're dealing with. If I'm asked to compute a limit at infinity on a polynomial function, then all I have to do is compute the limit at infinity on the leading term itself. Again, all of these lesser terms, negative 3x squared, x, and negative 12, matter a whole lot less as x gets larger and larger and larger. So maybe think about it like this. If x was like 1,000,000 and we're subtracting off 12 from 1,000,000, doesn't matter. It's still pretty close to 1,000,000, right? Or if we have 1,000,000 to the fourth plus 1,000,000, it's still really close to 1,000,000 to the fourth, right? Now, granted, the square and the square and the fourth power are a little bit more close to each other, but as far as out towards infinity, the fourth power is much larger than the second power. So that limit simplifies to that. Think about the leading term test if you need to. And then from here, we can kind of look at it symbolically. So let's say we forgot the leading term test at this point. We said, all right, well, x is getting larger and larger. Let's just look at it like this. What is 5 times infinity, a positive infinity, to the fourth power? It's still infinity, right? Infinity to the fourth is still infinity, times 5 is still infinity. So there you go. There's your limit at infinity equaling infinity. Again, it's telling us we have no horizontal asymptote, but at least on this side of the graph, as x approaches positive infinity, I know that function is doing this. Same thing with the limit at negative infinity. I'm just going to look at the limit as x approaches negative infinity and work with the leading term here, 5x to the fourth. So, put these things in symbolically if it helps. It's 5 times negative infinity to the fourth, and 5 times a negative infinity to the fourth would give us what?
Positive infinity.
A positive infinity, because the negative infinity to the fourth is now positive. Infinity times 5 is still infinity. Okay? So that tells us that as we go out in this direction, the function values are getting larger and larger in this direction.
So if the limit at infinity will always be infinity, hence our positive or negative.
On polynomial functions, always, yeah, that's true. Limits at infinity on polynomial functions will always be infinity, but only on polynomial, well, for now we'll say only on polynomial functions. And notice that's the same question. If I ask you what's the end behavior of this function, you say, well, it's a positive 5x to the fourth. The arrows do this, right? But those separate limits have told us that. Okay. So we sort of build all of that up, and we cut the limit stuff out, and we said, hey, here's the leading term test, because we didn't have the language of limits. Okay. Questions on that? Okay, so that's just another example. Hopefully that's pretty straightforward. If you have any questions, feel free to ask. But the idea here is, we kind of have to shift in how we think about stuff. Just in general, when it says determine the end behavior, of f of x, then what we do is we compute two things. One, the limit as x approaches infinity, and the limit as x approaches negative infinity. So that's, those two limit statements are implied in the phrase determine the end behavior. We've seen with polynomials that there's two sets of arrows, right? If you compute the limit at positive infinity and just get that one arrow, you've done you found half of the problem of the end behavior, right? There were functions that we looked at previous to this course that it makes sense to only look at one, positive or negative infinity. Can anybody think of those? What functions would it? When it says find the end behavior, would one or the other suffice?
Square root of x.
Square root of x, yeah. So functions that have restricted domains, like even roots, logarithms, yeah. What else? exponentials. Okay, well, sorry, we'll talk about it later. So this is kind of that summary. So the definition here says that if f, what we've worked with polynomials, if the function values become arbitrarily large as x becomes arbitrarily large, that's a hard word. Then we write this. But in other instances we saw in our previous examples, we could approach positive or negative infinity, and so could the function values. So that they're all written out here. Just, any scenario. And, to reinforce the definition, just think about these images here that are provided. Okay. So does all that make sense? Does anyone have any questions over that? I hope that this is, more in line with stuff that you've seen before this class. Just kind of like I said, just putting a limit to the process instead.
Are we going to go more in depth into when there is an actual solid answer?
Yeah.
Whether it's f of x, that's x approaches a, that f of x equals L.
Yes, yeah, we'll definitely see those as well. Okay, so here's a theorem, which means all of these things are true. All of these things, we can think about what we've just done with polynomials. So if we have an even degree, like x squared or x to the 10th, then the limit as x approaches positive or negative infinity is always positive infinity. So, if we go back to our leading term test, then it's that thing. It's positive infinity when x approaches infinity, negative infinity when x approaches negative infinity for the odd degree polynomials. So again, there, maybe think about this in behavior. All right. Item 3 is what we mentioned kind of in passing on the very first page. So if we have a reciprocal of a power function and we approach positive or negative infinity, then the entire thing approaches 0. The numerator is fixed at, that could be 1, that could be 1,000, that could be 10 to the 10th, whatever. But the numerator is fixed, the denominator is getting larger and larger, therefore your quotient gets smaller and smaller. That's what number 3 is saying. And number 4 is kind of what we just summarized. The limit on a polynomial is equal to the limit on its leading term, which is either positive or negative infinity, depending on the degree and the sign of the leading coefficient. So really this theorem that's, it's, the proof is, maybe the proof is not in the book, I'm not sure. But the proof of that is really what's giving you the leading term test. So this thing right here is your leading term test. Leading term test. It's just putting a very specific notation to what the leading term test actually is. That's it. All right. Is that stuff okay? Are there any questions on any of those? Okay, so then we've talked about polynomials, then we can talk about what happens when we start dividing two polynomials. And specifically, the stuff with polynomials mentioned in item 1, 2, and 4 here. And the rational function type stuff comes with number 3 as well, because then now we're dividing by polynomials too. So we've got this power function on the bottom as well. So the limits at infinity for rational functions, they have at most one horizontal asymptote. So these are the other functions that I was trying to get someone to mention, where it doesn't matter which limit that we, infinity or negative infinity, that we compute. So think about like rational functions for now, like they're the exception. Like if the thing says find the end behavior or determine the end behavior, In most instances, you're going to compute both of these limits. But in the instance that you're dealing with a rational function, both of these limits are going to be the same. And if you don't want to remember that, that's totally fine. If you just want to remember in behavior means compute both of these limits, so you're always sure, then by all means do that. So in order to evaluate limits at infinity on rational functions, the easier way is to use limit laws and methods for computing limits at infinity on polynomial functions, right? So a specific example to illustrate what I mean there, for example, the limit as x approaches infinity on 2x cubed plus 3x squared minus x minus 1 all over x cubed plus 5x minus 12. We said provided that the limit is not 0 in the denominator, when I look at the limit of a quotient, the limit law that I'm kind of utilizing is what? How else can I write this limit here?
So this one we could just do 2x cubed over x cubed?
Yeah, right. So you remember the limit law that says if you take the limit of a quotient, that's equivalent to taking the limit of the numerator and dividing that by the limit of the denominator. Right. So I'm going to write this out fully once, and just to show you what's happening, and it really doesn't arise this way in practice, but just to kind of tie into the limit laws and what we just talked about. This is the limit as x approaches infinity of the numerator all over the limit at infinity on the denominator. So when we look at it that way, then we say, well, the limit in the numerator is simply a limit on a polynomial. Limits at infinity on polynomials, all we have to do is work with the leading term. So this is now the limit as x approaches infinity on 2x cubed over the limit on x cubed as x approaches infinity, right? Just because they're both polynomials. It's important to remember that with these types of polynomial functions, looking at the leading term in the sense of a limit, it's only valid if you're approaching infinity or negative infinity. If you're approaching anything else, you have to look at the whole function. Is everyone clear on that? If I say what's the limit as x approaches 0, you wouldn't just say, well, what's the limit as x approaches 0 on 2x cubed? It's only at infinity that we're allowed to look at the leading terms. So, in essence, what that, kind of bypassing those limit laws now and just looking at this like this is the limit at infinity on 2x cubed over x cubed. And what is that limit? If you just look at infinity from here, then yeah, you'll say, well, it's infinity over infinity, right? But algebraically, we know 2x cubed over x cubed simplifies to 2. So that in practice, to deal with rational functions, the easy way is to just look at the leading term in the numerator and the leading term in the denominator, simplify if you can. Sometimes you have an actual limit to compute, as we'll see, but that's the easiest way to do those for rational functions. And what does our work mean?
Means you have a horizontal asymptote y equals 2.
Okay, good. the limit at infinity as x goes on and on forever that way, what do my function values approach? They approach 2. So like, you know, whatever the function's doing, we're just saying as we continue on, eventually the function values will approach 2. So we have a horizontal asymptote. Thus, f of x, I think we called that, has a, abbreviate that, horizontal asymptote at a y value of 2. So maybe let's see one. We'll look at, I think, yeah, this last example, and then we'll talk about the quote-unquote harder way to do these. But let's evaluate this here. What's the limit as x goes to infinity on 3x plus 2 over x squared plus 1? Maybe pause there for a second. Go back up to this function. Remember when you were given a function like that and it said determine the horizontal asymptote? And you said, all right, well, what's the degree of the numerator versus the degree of the denominator? When the degree of the numerator and denominator were the same, we took the leading coefficient divided by the leading coefficient, right? So we said, well, the horizontal asymptote here is going to be at 2 divided by 1. The horizontal asymptote is at 2. Okay. So that's the same thing, same conclusion we got here with the limits. So in essence, the 3 cases you have to remember, well, the degree of the numerator is less than the degree of the denominator. What exactly did that mean? I don't know, I don't remember, I don't care. Now I have a limit, and that will tell me exactly what's happening. So if you look at this function and say, well, the degree of the denominator is larger than the degree of the numerator, but I don't remember what that meant in terms of a horizontal asymptote, then we'll just compute this limit, and it'll tell us, since it's a rational function at infinity, all I have to do is look at leading term in the numerator divided by the leading term in the denominator. Simplify that, and then if there's still an x, then I'll just compute that limit. That's the limit as x approaches infinity on 3 over x. So then this is where that property number 3 comes in. Yeah, question?
So would that be 0?
Yep.
As our answer?
Right. So I want to point you back here to property number 3, where it says that if we're looking at a power function, rather a reciprocal of a power function, then that limit's 0. Because when you think about it a different way, the numerator is 3, but the denominator keeps getting larger and larger and larger. 3 divided by a very large number is a very small number. So this is 0. So when the degree of the numerator is smaller than the degree of the denominator, you always had a horizontal asymptote at y equals to 0.
That's the same thing we learned in pre-calc.
Yeah, exactly. Yeah.
Because the exponent at the bottom is larger than the one on top, so
Yeah.
it's always 0.
So it's always 0. But now we see why it's always 0. Yeah.
It's nice that they told us that last. Who shows why then?
Yeah. So yeah, I hope some of this stuff is familiar. Depending on how long ago it was for you, it should be relatively familiar. But so there we go. All of those criteria for finding horizontal asymptotes. Really, in effect, you don't need to remember them anymore because all you have to do is compute a limit at infinity, and it'll tell you where the horizontal asymptote is. Yeah.
I was going to say, what happens if, say, you have, like, especially for the denominator, what happens if you have 2 leading terms, or 2 leading coefficients?
In the numerator, what do you mean?
Like,
In the numerator or denominator.
in the denominator, like, say, instead if you had 2x cubed, and underneath you had, like, 4x cubed plus x cubed, something
Oh.
like that.
Yeah, so then there I would just combine those terms. You have 2x cubed over 5x cubed. So then you would have a horizontal asymptote at 2 over 5. Yeah.
And
may have missed it with his writing, but how do you get 0 out of 3 over x if the limit as x approaches infinity?
Because this is on the bottom. The bottom is getting larger and larger. So you have 3 over a really large number. Like 3 divided by 10.3, 100.03, 1,000.003, right? So it just keeps 0.00000003.
Okay, so it's approaching 0.
Yeah, it's approaching 0. Yeah, again, the limit is approaching, right? X is approaching something. What is y approaching? And that's totally solidified when we think about the nature of a horizontal asymptote, right? If all a horizontal asymptote here meant was that the function gets closer and closer to as it continues on, right? Yeah, in some instances, do y'all remember when your function actually crossed the horizontal asymptote, right? So, you know, what sense can we make of that? Like, what if I had this horizontal asymptote? I don't know if you saw a whole lot of functions, but there were functions that crossed the horizontal asymptote, maybe even more than once. So how do we make sense of that? Like, why did that happen? If we say like the limit as x approaches infinity on this function, the y values are getting closer and closer to 0, then how come it crossed the horizontal asymptote if we mean that it's getting closer and closer to 0?
Because we're only concerned with the end behavior.
Right. Yeah, exactly. So this is the limit at infinity. This says when x is way out here, what's happening? What's the predictable behavior way out here? Right? It's not saying like, you know, around from 0 to 100 what's happening. It's saying that we know if I keep moving indefinitely and never stop, that the function will just keep getting closer and closer to 0. It doesn't tell us anything about these smaller values. So that's why you don't see that in the limit either, because we're only talking about values way out here. Does that make sense? Any questions?
Is there a thing to determine like when it hits that terminal spot where it finally hits?
Yeah, so to find where your function, if a function crosses the asymptote, let's say that this is an asymptote of y equals to 3, then I would just set my function equal to 3 and solve for x. And you can get like 1 or 2 values out of that.
Choose an intercept kind of thing.
Yeah, exactly. So the harder way, the thing with the easy way, technically it's only applicable to rational functions. So like, we'll see an example like this later, but like 3x squared minus 1 over the square root of x to the 6th plus 4, that's not a rational function anymore because of the radical on the denominator. So that's an example of something that's not a rational function, and there's many others, but the harder way it is the general approach to, like, if you have a quotient, any quotient that you're computing the limit at infinity on. So in general, to compute any of the limits at infinity, like f of x over g of x, and we have to divide all terms in the numerator and the denominator by the highest power that occurs in the denominator. So that's kind of a mouthful, but basically what we're saying is that if, you know, the harder way, in order to compute this limit, I'm going to identify what's the highest power of x in my denominator, x squared, and then I'm going to divide everything by x squared. Because, I mean, that's in fact what you're really doing, isn't it? I mean, all of this is divided by x squared minus 1 as x goes to infinity. We're essentially dividing by x squared, right? There's extremely large numbers minus 1. They're still extremely large numbers. So this is going to look like 3x divided by x squared plus 2 over x squared. Do that just yet. 2 over x squared. In the top, all divided by our x squared over x squared minus 1 over x squared. So we've divided everything by the highest power of x in the denominator, and then we simplify. That's the limit at infinity. 3x over x squared is just 3 over x. Can't simplify the positive 2 over x squared, so we'll leave that. X squared over x squared is 1, and we can't simplify the minus 1 over x squared. So remember then, the limit laws are handy here because you're computing the limit of a quotient. So I can look at the limit of the top and the limit of the bottom. And when I do that, I'm also looking at the limit of a sum and the limit of a difference. So really that limit is just operating on each term individually. So what is the limit as x approaches infinity on 3 over x? This is 0. Limit at infinity, limit at infinity on 2 over x squared. Also approaches 0. Limit at infinity on 1. That approaches, this approaches 1. And the limit at infinity on negative 1 over x squared approaches 0. So let's put that together. We have 0 plus 0 all over 1 minus 0. That's what we're looking at. Which of course is 0. So of course is what we had prior to. So I don't know, I just say that's the hard way because it's just a little more involved. It's not, I don't think that it's harder, it's just more work. Yeah.
Question about the hard
Sure.
versus easy. If I learn just to do the hard and I apply it to everything that we used on easy, it will still work?
Yes.
Okay.
Yes, the hard, this hard method, if you will, it works on all functions f divided by g. The easy route that we took we're only applying that to rational functions.
Because I'm concerned about my brain capacity, so I'm going to
Sure,
go with
yeah.
one that works for
Yeah,
everything.
yeah, definitely a legitimate concern. Let me see, do we want to, okay, so just evaluate this. It doesn't matter what method you use, but evaluate that using calculus because it is a limit. So what y'all get?
Infinity.
The limit as x approaches infinity is equal to infinity. Does everybody agree with that? So you can do it the hard way or the short way. This is equivalent to the limit as x approaches infinity. We'll look at just the leading terms. 3x to the fourth over 3x cubed, and then simplify. So that's just the limit as x approaches infinity on x, which is equal to infinity. Okay, so what does that mean? The function, 3x to the fourth, etc. What does that mean about that function? Yeah, the end behavior is up, right? In other words, it doesn't have a horizontal asymptote. Right, there is no horizontal asymptote here. So with a limit at infinity, we have covered all three scenarios for horizontal asymptotes. Degrees are equal, leading coefficient divided by leading coefficient, y equals 0, or there is no horizontal asymptote. Those are the only three outcomes with horizontal asymptotes for rational functions. y'all have any questions on any of this? That's sort of similar in the previous one. Does anyone remember this scenario in sense of like an algebra pre-calc perspective? Yeah, so is there a horizontal asymptote here? We'll ask that question first. No, because the limit goes off to infinity. As we said, the degree is higher than the top, so we end up with infinity as the limit. But when the degree of the numerator was 1 higher than the degree of the denominator, what happened?
We have no oblique asymptote.
Oblique asymptote or a slant asymptote, a linear asymptote that's not horizontal. Do y'all remember those? So how did you find those? How did you find the equation of a slant asymptote? Close. You had divide. Yeah, we divide all of it. So this, we'll mark here that this limit is infinity. That means there's no horizontal asymptote. But let's look at this function in a different way. Let's take the 2x squared plus 6x minus 2 and divide that by x plus 1. Really, this is what we have above this line. That's it for us. Unless it specifically has you analyze the oblique asymptote. Generally, we're just computing these limits and wanting to know what that means for us in terms of that function. Okay. So we're going to divide x plus 1 into all of this. We have to multiply the x by a 2x in order to get the 2x squared. So 2x times x is 2x squared. 2x times 1 is 2x. And remember, then we have to subtract all of this off, just like if it were a number and when we're doing long division. So then we have 0. We have 6x minus 2x. And then we bring down the next digit, if you will, the next term. We have to multiply then this x by 4 to get this 4x. And then the 4 times this 1 is a positive 4. And we subtract all of that. So we have a minus 2, a minus 4, minus 6. And then that was our remainder. And that was our quotient, right? So in pre-calc, you stopped with that quotient and you said, all right, well, my quotient's 2x plus 4. Therefore, the equation of my slant asymptote was 2x plus 4. Okay. All of this stuff that we've just done, 2x means 2x squared plus 6x minus 2 divided by x plus 1 is actually equal to what? 2x plus 4? Is that it? Minus 6? Is that it?
6 over x plus 1.
Yeah. Yep. Very good. 6 over x plus 1. Okay, so what? Big deal, right? Well, back to the limit. What that means is that the limit as x approaches infinity on 2x squared plus 6x minus 2 all over x plus 1. We now know that function is equivalent to this one over here, so let's rewrite that as such. And then we can look at it in a slightly different way. Our conclusion is still going to be the same, but looking at slant asymptotes in terms of limits to see how they actually arise, other than just, hey, to find the slant asymptote, divide it, right? That's helpful because it finds the slant asymptote for you, but it doesn't really tell you what's happening. Like, why is that? As x approaches infinity, what does this approach? What?
0.
0. Again, it's 6 over a very large number. That approaches 0. So this is kind of essentially the same thing. What it's saying is that as x approaches infinity on this function, for large values of x, this function behaves like this function. Yeah, the 2x plus 4 is going off to infinity, but we see that as x gets larger and larger, the 6 over x plus 1 approaches 0, so it's not contributing anything to the behavior of that function at all. What's contributing to the end behavior of the function is that linear piece, the 2x plus 4.
So all that's saying is that really that part right there is all that's really important to this equation.
Yeah. That's how the function behaves at the very ends. Yep. So we'll graph that and pick back up on Thursday. The notes, I'll post the incomplete notes in the video if you need to review them over the long weekend, but we'll meet back up on Thursday.